This is now our fourth video looking at using integration to find the area trapped between a curve and the x-axis. In the first question, we're told the diagram above shows the line with equation y is equal to 9 minus x and the curve with equation y is equal to x squared minus 2x plus 3. The line and the curve intersect at the points A and B, and O is the origin. In part A, we're asked to calculate the coordinates of A and the coordinates of B. We're then told the shaded region R is bounded by the line and the curve. In part B, we need to calculate the area of R. Okay, so what we've got here is y is equal to now 9 minus x. We've also got y is equal to x squared minus 2x plus 3. Now, if y is equal to 9 minus x and y is equal to x squared minus 2x plus 3, then these must be equal. So we can say x squared minus 2x plus 3 will be equal to 9 minus x. So we're simply solving simultaneous equations to find the coordinates of A and B. So if I add x to both sides, x squared minus x and subtract 9, minus 6 will be 0. That will factor, we'll have x plus 2 multiplied by x minus 3, and that will be equal to 0. So we can see x will be equal to negative 2, or we've got x equal to positive 3. So by looking at the graph now, we can see that A has the x coordinate of minus 2, B has the x coordinate of 3. So all I'm going to do is find a y coordinate. So I'm going to sub this in right here. So putting it into the linear, we've got now from here that y will be equal to, now 9 minus minus 2, so y will be 11. If we consider if x is 3, y will be 9 minus 3, so y is going to be 6. So we can say now that A has the coordinates minus 2, 11, and B has got the coordinates now 3, 6. So that's the first part done. Okay, we now need to find the shaded region R. We've got two different methods that we can use. I'm going to run through both of them. The first one is to find the area of a trapezium and now consider the area under a curve. So the first method is to draw a trapezium. The trapezium is going to come down and it will be a perpendicular from A to the x-axis. We will then come across, I will drop a perpendicular from B down to the x-axis. I'm now going to draw a line like so. Now if we consider just jotting this to the side, what I'm going to have, let's just straighten it up. We're going to have something that looks like this. Now this doesn't have to be accurate, but it'll give us some idea of what we've got. So if we consider now the difference in the x coordinates, we've got now minus 2 and 3. This is going to be 5. I'm going to put a right angle here. So we've got now here minus 2 and we've got here positive 3. Okay, if we consider now the y coordinate of A, that is going to be 11. So this is 11. The y coordinate of B is going to be 6. So if you want to put those on, you can do that. If we look at the area of a trapezium is given as now 6 plus 11, so 6 plus 11, divided by 2, multiplied now by the perpendicular height, which is 5. So 17 over 2 multiplied by 5, the area will give me now 85 over 2, and that will be units squared. Okay, I only want now this region R. I can find the area trapped under the curve between now x is equal to minus 2 and x is equal to 3. If I find that area using integration, I can simply now subtract this away from the area of my trapezium. That will leave me with R. I'm going to call this region here S, and I'm going to say that S will be equal to the integral from negative 2 to 3 of my curve. My curve is x squared minus 2x plus 3. So I'm going to go ahead and integrate this with respect to x and then evaluate. So I can say from here now that s will be equal to, and I'm going to do this fairly quickly. In the exam, show clearly how you're doing this. S is going to be 1/3 x cubed. I'm integrating. Raised by a power, divide by the new power. Now I'm going to write this as minus x squared. In the exam, show exactly how you've done that. Plus 3x, and we're interested in this from negative 2 to positive 3. So subbing that in, I can say that s, and again show this clearly, that's 3 cubed, which is 27. 27 over 3 is 9. Then we've got minus 3 squared, which is minus 9, which is nice, and then plus 9. Okay, now let's sub in minus 2. That will give me minus 8 over 3. Then I'll have now minus 4, and then we'll have minus 6. So as we've done in previous videos, I'm going to evaluate, and this is going to give me the area, and that's for region S. That is what is trapped under the curve between these 2 points. So let's go ahead and work this out. What we've got here is the following. So S is going to be equal to 9. So we got 9 minus, and then we're going to have what's left in here, minus 8 over 3 minus 10. I'm just going to put that through a calculator to find S. So let's do that then. So what we've got then is 9 minus, and then we're going to have minus 8 thirds. So minus 8 thirds minus 10. So minus 10. And that's going to give me now 65 over 3. So we can say then that S will be equal to 65 over 3, and that's going to be units squared. Now what I want to do to find R is going to be this value minus 65 over 3. So we can say that R, the shaded region, will be now 85 over 2 minus the 65 over 3. This is the total trapezium, this is the area under the curve. So in the calculator, I'm just going to do that and subtract those away. So what we're going to have then is 85 divided by 2 minus the answer that I've just found, and that will give me now 125 over 6. So R is equal to 125 over 6, and that's going to be unit squared. You won't be penalised for leaving off unit squared. So there we go. Now, that's the first way of doing it, and that's perfectly fine, and that's the general way. If you're confident there is an alternative approach. Now, if we've got these 2 points of intersection, these clear points of intersection between the line and the curve, and this is absolutely vital, what we've got is this point right here and this point right here, which you already know. What we can do is consider now the integral. The integral is a summing tool. So I'm going to sum now the area under the curve and also the area under, or the area of the trapezium. Now we're going to be subtracting these away. So logic says that we can just subtract them and integrate anyway. Now if I look from A to B, we can see that the curve is below the line. So what I'm going to do is integrate now the line and subtract away the curve in one go. So what I'm going to say here now is R will be equal to the integral, and we're taking it from the same values of minus 2 and 3, and I'm going to take the line which is 9 minus x. I'm going to subtract away from it now the quadratic, and this is going to do it in one go. So minus 2x plus 3. We need to be a little careful right here in terms of our subtraction, as we got some negatives in there. But we can go ahead and do this and just evaluate it. So what I'm saying is I'm going to take away, as I'm doing my summation, with really quite a mechanical process, we're going to be taking away the area under the curve from the trapezium. So what we've got then, R will be equal to the integral from negative 2 to 3. So I'm going to have minus x squared. So putting these now in descending powers of x, then I'm going to have now 2x minus x, which is going to be now, that's going to give me plus x. If I now consider I've got minus 3 and 9, that's going to give me plus 6. So all I'm going to do is integrate this and then put through the limits. So R will be equal to, and again, all I'm going to write now is the following. We're going to have minus 1/3 x cubed plus 1/2 x squared plus 6x, and I'm interested in this now from negative 2 to positive 3. So let's go ahead and look at that. Let's say R will be equal now, and show this clearly in the exam. That's going to be now, if I sub this in, we're going to have now minus 9. Then we're going to have plus 9 over 2 plus 18. From that, I subtract and evaluating 2. That's going to give me 8 over 3. This is now going to give me plus, and that will give me plus 2, and then we're going to get minus 12. So let's go ahead and do that and put it all through the calculator. Show clearly how you're doing this. I've been a bit lazy and not showing the examiner, and I'm assuming that you'll be able to do that. What we're aiming for though is this same value. So what we've got then is the following. We've got minus 9. So minus 9, and then we've got plus 9 over 2, or 4.5 if you like. And again, you can tidy this up with a bit of mental maths. And then we'll subtract away from that now. We've got 8 over 3. And then we've got now essentially minus 10. So minus 10, and again you can tie that first bracket up, and we get 125 over 6. So there we go. R is equal to 125 over 6. So I've used an alternative method. I've relied on the fact that the integral is a summing tool and just said, well, the line is above the curve. We'll subtract the curve away and that will give us what's left over. Now, you have to be very careful with this. So another example might be, let's just draw some form of quadratic. Let's have a quadratic. And let's say we've got something like this. Let's say that's a quadratic and we've got now some line. If we have a line and it went through there, we've got these points of intersection. Now this time we might want this area right here, okay? So all we would do is to find this area, and let's call this region R. We'd find the points of intersection. At this stage now, the curve is above the line. We would find now the equation of the curve, we would subtract away the equation of the line, we would integrate between these two limits. So let's say this is x1 and this is x2. So all we would do is take the curve. So let's say now, let's just say the curve, let's say the curve is y is equal to the f of x, and let's say the line y is equal to g of x. So what we'd do is the following. We would do the integral from x1, so let's write x1 to x2, now of f of x minus g of x. So we just subtract them, integrate from there with respect to x, and evaluate the limits. But you have to be careful. Do check that these points are intersecting. Alternatively, with that one, all you would need to do if you wanted is just, again, integrate the curve from here to here, and then subtract away that triangle right there. So, two different approaches to the same question. Okay, let's move on. Hopefully you see that that holds both ways. Let's look at this one. We're told the diagram above, which is now to the left, shows part of the curve C with equation y equals the f of x, where the f of x is x cubed minus 6x squared plus 5x. The curve crosses the x-axis at the origin and the points A and B. In part A, we need to factorise f of x completely. So as we can see, we've got this cubic equation right here, and it's got a common factor of x. So we could actually write the f of x, taking a common factor of x out, leaves me x now, then I'm going to have x squared minus 6x plus 5. Again, I can factor this further. I've got a linear factor and a quadratic factor. Let's express this quadratic factor now as two linears. So what's that going to be? X minus 1 and x minus 5. So that's what we've got. That's fully factored. So all I've done is taken the common factor of x out, which tells us now that if we set this to 0, we got a solution at 0, 0, and then these two now consider A and B. So write down the x-coordinates of the points A and B. So if we set this now, let's just set this equal to 0, so x minus 1, and then x minus 5. So if this was equal to 0, we could see now that x would be 0, which corresponds to the origin, x is 1, or x is going to be 5. So we can say now that A, and all they want is the x-coordinate. I'll just put in that this is going to be 1, 0, and then we can have B, and that will be 5, 0. So your answer essentially is 1 and 5. Okay, in part C, we're asked to find the gradient of C at A. So at the moment, we've been doing the integration, but the question's now switched over to differentiation. So all we're going to do is just answer this. So let's take the f of x. The f of x is x cubed minus 6x squared plus 5x. So if we want the gradient now, we want the gradient function. So the derivative is going to be f dashed of x. So f dashed of x, multiplied down by the power and drop the power by 1, 3x squared. Multiplied down by the power and drop the power by 1, multiplied down by the power and drop the power by 1. So what we can say then is the derivative for gradient function is going to be f dashed of x, which is 3x squared, minus 12x plus 5. So what we can do then is look at point A. Now we know A has the coordinate here, and that's going to be 1, 0. So all we're going to do is f dashed of 1. We just simply sub this in, so f dashed of 1. So we're going to get 3 lots of 1 minus 12 lots of 1 plus 5. So what's that give me? Minus 4. So we can say f dashed of 1 is going to be now minus 4. And that looks reasonable. We can see again that if I have the gradient just here, let's just put that on. Let's say we have now tangent just there. That's reasonable. That's believable. If we had now, and it was this point right here, and we were going in this direction, quite clearly a negative answer is not going to be right. But that's a reasonable answer. Okay. We're now told the region R is bounded by C and the line OA, and the region S is bounded by C and the line AB. In part D, it says use integration to find the area of the combined regions R and S, shown shaded in the diagram above. Okay, they've been kind to us. What often might happen is that they give us now the integral and they say find the area now trapped between the curve and the x-axis between these points of intersection on here. But they've shown us now. And this goes back to one of the problems that we looked at before. If I integrate it straight the way through, I've got a negative area, which is going to be S, and I'm going to add that to the positive area. What we need to do is split this up. We need two distinct regions. Now we know that the integral will give us now the area. So I'm going to say the area R will be equal to the integral from 0 to 1. So we're interested now, this remember, O is 0, 0, this is 1 and this is 5. So we want the integral now, and all we're going to do is this right here. So the integral of x cubed minus 6x squared plus 5x, and we're integrating with respect to x. Now, consider this area. This is going to give me a negative area. So I'm going to say that S will be the modulus. And the modulus is the absolute value. So whatever area I get, or whatever value my integral gives me, I'm just going to make positive. So this is the integral now from 1 to 5. And again, it's just x cubed minus 6x squared plus 5x. We're going to be integrating with respect to x. We're going to get a negative value, which is perfectly fine. And we're just going to take the absolute value of that. So let's go ahead and integrate this. Let's integrate this. So what we'll say then is I, the integral, and I'm going to do this fairly quickly. I'm just going to write now 1 over 4x to the 4th. In the exam, show clearly what you're doing. Minus raised by a power, divide by the new power, which will give me minus 2x cubed. Plus now 5 over 2x squared. So this now is my integral. So do show in the exam that you've raised by a power and divided by the new power. So let's consider R. Let's find the area of R. So R, we're going to have now 1 over 4 x to the 4th minus 2x cubed plus 5 over 2 x squared. And we're going to take this now from 0 to 1. So let's go ahead and sub that in. And this will give us a positive value. So R is going to be now 1/4 minus 2 plus now 5 over 2. And then all we do is subtract away 0 plus 0 plus 0. And you do need to show that you're evaluating 0. Okay, so what's that? That's going to give us now, what have we got? We've got 2 1/4, which is 9 over 4. So this is going to give me now R will be equal to, just subtracting, that's at half. Let's just, in fact, let me put, I don't know why my brain's not working. Let me put that for a calculator. 0.25 minus 2 minus, sorry, plus 2.5. So plus 2.5, what's it going to give me? 3/4. Okay, so R is 3/4. So that's that area right here. Okay, so we found that one. So positive value, and we can say now that this area is going to be 3 over 4. So that one right there, nice and straightforward. Well, not as straightforward if you can't manage to add it up like I didn't. Okay, now what we've got to do is consider S. And I'm going to be clear with this. S is going to be the modulus. So we're going to get the modulus. And what we've got then is the following. Again, we've just got 1 over 4 x to the 4th minus 2x to the 3rd plus 5 over 2. And then we're going to have x squared. And we're interested in this now from 1 to the value that we've got just here. And the value is here. B, we've got the x coordinate for B of 5. So we're going from 1 to 5. Now what you'll recognise now is that if we evaluate 1, this is what we have just here. So we can sub that in. Okay, so what we can say then is S will be now the modulus. And putting in 5, what I'm going to have here now is 5 to the 4th over 4. 5 to the 4th is 625. 625 over 4. Minus now, 5 cubed is going to give me 125, so that's minus 250. And then we're going to have now plus 125 over 4. Okay, now, so over 2. Now all I'm going to do is subtract away from that, because we've already evaluated 1. I'm just going to subtract 3/4. Again, in the exam, make this 100% clear. I'm essentially just making life slightly easier. So let's go ahead and do that. Let's put that in there. So what we're going to have is the following. So I've got now 625, and again, a bit of mental maths if you want to tidy this up in your head, but don't lose marks just to do it in your head. There's no prizes. It's all calculator. Plus now 125 over 2, and then what are we going to have? Minus, and then we'll subtract away that 3/4, so minus 3/4. So this is going to give me now a negative value and that is going to be negative 32. So we can say then that s will be equal to the modulus of minus 32. So we can say that s will be equal to 32. All it's saying now is the reason it's negative, it's because it's below here. So what we've got then is the following. We've got this area, and this is going to be 32. So we've got now 32 just here, and we need to find the area. Now usually it wants the exact area, so we're going to state the exact area. So what's that going to give me? 128 over 4 plus 3 over 4. So let's just add those two together. So what we can say then is the combined regions now are going to be 3 over 4 plus 9. If I multiply this and put this in 4, so I've got 128 over 4. So 128 over 4, and that's going to be 131 over 4, and that will be units squared. Again, you won't be penalised for the lack of units squared, but essentially that's what we're doing. So we look at this as two distinct areas. If you're in a situation like this, do sketch a curve. Once you sketch a curve, it should become quite obvious, if you've got points of intersection, that you're going to have some curve below the line, which will give you a negative value, and some above the line. So quite a nice question, and for some reason at this point right here, they completely flipped the script, as it were, and just said, well, find the gradient. That's just, I suppose, it's just a part of it. Sometimes we'll use the tangent to find certain areas, but this kind of doesn't really have an awful lot to do with what we're going to do from that point on.